The capacitor. Capacitors are one of the fundamental passive components. In its most basic form, it is composed of two plates separated by a dielectric. The ability to store charge is the definition of capacitance. The charging process. We have a dielectric. You have electrons, negative charged electrons on one side, positive charged electrons on the other side. When you attach the battery, the negative electrons are moved away from the plates, go through the battery, and are reattached on the negative side of the plate. And this will keep happening until the potential across both plates are equivalent to whatever the battery is. Capacitance is the ratio of charge to voltage. So the formula is Q divided by V. Rearranging the amount of charge on a capacitor is determined by the size of the capacitor and the voltage. For example, if a 22 microfarad capacitor is connected to a 10-volt source, the charge is 220 microcoulombs. So that's basically just plugging in 22 microfarads and times 10 volts and doing the math. Oops. Parallel capacitors. When capacitors are connected in parallel, the total capacitance is the sum of the individual capacitors. So this is the general equation. You just add the capacitors. Notice the parallel connection, they're end to end. So if a 0.001 microfarad capacitor is connected in parallel with a 800 picofarad capacitor, the total capacitance is 1800 picofarads. So 0.001 microfarads is 1000 picofarads plus 800 picofarads gives you 1800 picofarads. Now notice that parallel capacitors are similar to series resistors as far as the math is concerned. Series capacitors are connected, or the formula is similar to parallel resistors. So you have to go 1 over the capacitance values and then add those all up and then inverse. Or if you only have 2, you can use the product over sums rule. For example, if a 0.001 microfarad is connected in series with the 800 picofarads, the total capacitance is 444 pico. So this is found by taking 1 over the 1000 and 1 over the 800 to get 444 pico. Now notice the total capacitance is smaller than the smallest capacitor. Capacitors in DC circuits. When a capacitor is charged through a series resistor and DC source, the charging curve is exponential. So this right here is an example of a charging capacitor. And this right here is a decreasing exponential curve, and this is what happens to the current. The current starts out high, and as the capacitor reaches its charged value, or whatever the source is, basically you have no current flow. The capacitor is seen as open in the circuit. When a capacitor is discharged, so it starts off as the charged voltage. Notice I do not have a source here. The capacitor is just charging through the discharging through the resistor. The voltage follows a decreasing exponential, so it starts off at whatever value it was and decreases to 0. And notice again the current has the same path. So whether you're charging or discharging a capacitor, the current still follows the same path. If I attach a pulse waveform here, where the voltage goes up and down at a constant interval, what happens when the voltage is up here at the peak value, let's say that was 10 volts, this capacitor will charge up to that value, assuming we have enough of time. And over here, when the voltage is off, we have a discharging capacitor. Charging, discharging, charging, discharging. Now what happens with the resistor voltage will follow the path of the current. So when the voltage first starts off, capacitor is 0, so all the voltage has to appear somewhere. It appears across the resistor. You still have to use Kirchhoff's voltage law. As the capacitor begins to charge, the resistor voltage begins to decrease because the sum of the two voltages still has to equal the source. When you reach the maximum, the resistor is 0. As the capacitor discharges, all of that voltage of the capacitor is seen across the resistor, so that's why it follows this type of curve. So this is the universal charging and discharging. This is the increasing exponential. This is the discharging. And at certain time intervals, you know what percentage of voltage that the capacitor is going to be at. Now each time interval is expressed by the resistance times the capacitor value. Reactance is the opposition to AC voltage. Basically it's an ohm number, and you just would plug in the frequency and the capacitance value, and you would get what type of resistance this capacitor is exhibiting in that circuit. When a sine wave is applied to a capacitor, there is a phase shift between voltage and current, such that the current always leads the voltage by 90 degrees. Capacitor, a fundamental component that has two conductive plates separated by an insulating region called the dielectric. A capacitor has the ability to store an electric charge. The dielectric is the insulating material that is between the conductive plates of the capacitor. Capacitance is the ability to store charge by an electrostatic field. A farad is the unit of capacitance. 1 farad is the capacitance when a charge of 1 coulomb is stored with a potential difference of 1 volt across the plates. Relative permittivity, a pure number that compares the effectiveness of a dielectric to that of air, also known as the dielectric constant. Working voltage is the maximum sustained DC voltage that a capacitor can withstand.